Hi guys, and welcome to lesson 7.3 on rational exponents. We've already gone over multiplication exponential rules, and we've gone over division exponential rules. So this is our third big category of rules, in which case everything else for this chapter is going to build on the foundation of these three categories. Now in this video we're going to cover three main topics. We're going to cover vocab words, key terms, vocab key words, of radical and exponential functions. Specifically, how to recognize them and write them back and forth. So how to change and go from radical form to exponential form. Okay, that's number one. Number two is nth root. Okay, and this actually has three parts to it, so it'll seem a little long, but it'll go by pretty quickly. It's solving, writing, and complex nth roots. And then last but not least, at the very end, we will solve exponential functions, or exponential equations. So, a lot to look forward to. Let's get started. First, we're going to start with a basic review of how to solve radical equations. As a reminder, this is a radical, also known as a square root symbol. Now, for those of you who've forgotten, when you're doing a square root, when you're solving a square root, you are looking for the repeat factors. For example, the square root of 4 is 2, meaning that 2 times 2 is equal to 4. The same factor repeats, multiplies by itself, and gives you 4. If you want to go a little bigger, the square root of 25 is 5. Okay, so the same factor, 5 times 5, gives you 25. Now, only the repeat factors can come out of the radical. Okay, the square root only allows the repeat factors out. So you can almost picture the square root symbol as like a door, a gate. If it's a repeat factor, one of the terms is allowed to come out, and the other one goes away. So those are our basic ones. Those are the basic square roots. And of course, you probably know the giant long list, the square root of 9, the square root of 16. There's more than just these few. But what happens when you have a non-perfect square root? Because these are perfect. Okay, these simplify down to one number. So these are perfect square roots, or perfect squares. So what happens if it's not a perfect square? Now let's go up to number 1. If you're looking at this and you know your perfect squares, you know that 36 actually is a perfect square. But I'm going to show you how to do it the long way so that you can see the pattern I'm going to use. The way you solve for square roots is you bring the inside number off to the side. Whatever's inside, you bring it off to the side like this, and we're going to create a factor tree. So what are two numbers that multiply to 36? In this case, it's actually 6 times 6. So what I'm going to do, I have a pair, I have a repeat factor, so I'm going to circle one and cross out the other. The one I circled is the one that comes out. My answer to this problem is 6. The square root of 36 is 6. Now this whole circling and crossing out thing may seem a bit redundant, unneeded for perfect squares, and it kind of is, but when you get into your more complex numbers, it's very helpful. Let's go on to the next one. So again, I'm going to pull out 27. What are two numbers that multiply to 27? Well, that's 3 and 9. Two numbers multiply to 9, you got 3 and 3. Now remember, I'm looking for pairs of repeat factors, which means I'm going to circle one and cross out the other. This last one, this last 3, it doesn't have another pair, so it stays inside. So my answer to this is 3 root 3. And that is the proper way to refer to your answer. It's either 3 square root 3 or 3 root 3. Okay, take a moment, try to do the other two. When the video plays again, you'll see the answers. Okay, here are your answers. Now, in these last two problems, you had to deal with variables. The same rules that apply to numbers apply to variables. If it has a repeat factor, if there's two of the variable, well, then one of the factors comes out. If it doesn't have a factor or a pair, it stays inside the radical. So for number 3, there was only one m in the beginning of the problem, and so the m stays inside the radical because there isn't another pair. For this last one, number 4, we had m to the 4th power. So you can see I did a little factor tree for m. All right, and I actually went down all the way. You could have stopped right here when you saw that m squared repeated. So technically I could have done this number, and that would have been equally correct. But so that you can see what happened, I went all the way down. I had two m's, so that means two n's come out. And then, of course, my numbers behave normally. If you don't understand how to solve radicals and simplify radicals, please come and talk to me. That way I can explain things and give you some extra help. Okay, now let's get to rational exponents. A rational exponent is when you have basically a fraction exponent. Okay, so if you're following this example, let's just say I have b to the 1/2 power. Okay, let's say I have two of them. I have one b to the 1/2 power, and I have a second b to the 1/2 power. Well, if you were to add these fractions together, you would get b to the 2/2, which is b to the 1, or just normal b. So that means that when you have a fraction for an exponent, it becomes a radical, which makes a little bit of sense when you think about it. Let's just say I have 3 squared. Well, 3 squared is 9. Thus, it kind of makes a little sense that I have 9, if I have 9 to the 1/2 power, that I'm going to go down and get 3. Okay, if you don't understand this, don't worry. This is the topic. The rest of the PowerPoint is over. But just to remember, when you have a fraction for your exponent, it becomes a radical. And here it is again. The new information on this slide is this little bit right here. So it's not just enough to know that if you have a fraction for an exponent, then you can rewrite it as a radical. Once you rewrite it, you then have to simplify completely. It's a lot like multiplying fractions. Once you multiply your two fractions together, you're not done. You still have to simplify and make sure it's the smallest possible. Same thing with radicals. Once you rewrite your exponential form as a radical form, or in radical form, you then have to simplify your radical as far as you can. So let's go over and look at this problem. What I'm going to do is I'm going to bring 38 out, and I'm going to try to simplify this. I'm going to try to find repeat factors, or a perfect square, as I'll start calling them now. Okay, so this is 2 times 19. Okay, 2 is a prime number, 19 is a prime number. Neither one of these numbers go any further. So this answer is simplified as far as it can possibly go, because neither one of these numbers are perfect squares or will break down into perfect squares. Okay, let's practice. So I mentioned on the last slide, we have radical form and exponential form. Radical form means when it's written with the square root symbol. Okay? Exponential form means written with a base and an exponent. Okay? So the names actually clue you into what's going on. So these two problems are already written in exponential form. These are in exponential form. Whereas these are in radical form. What this question is asking us to do is rewrite the problem so that it's in the opposite form. So for this one, or for A and C, I'm going from exponential to radical. And then for D and B, or B and D, I'm going from radical to exponential. Here we go. So for this first one, let me erase, and let's solve. For this first one, remember, when I have a fraction as an exponent, I can rewrite it as a radical. So I can go ahead and rewrite this as the square root of 25. Now that I've rewritten it, I have to simplify. 25 times 25 is 5 times 5. I have a perfect square in there, so I'm going to circle one and get rid of the other. My answer to this is 5. Let's skip down and go to C. I'm still writing in radical form. Now, a rule that we've been going over and over when we did multiplication rules and division rules is that the exponent only applies to the base. Same thing applies here. Even though it's a fraction, my exponent still only applies to my base. In this case, my base is x and only x. Okay? That means I'm going to rewrite this with only the base inside my radical. My 5 is going to stay outside because it's not affected by my exponent. And that's my answer. Now, the way it would look like if both were in the base, it would be in parentheses. If it was in parentheses, then you could put both inside the radical. But always remember, the exponent only applies to your base. Okay, let's go over to examples B and D now and rewrite these in exponential form. Erasing. All right, here we go. So when we're doing this, we need to remember that whenever there's a square root, okay, the square root equals the fraction 1/2. So this is 18 to the power of 1/2. Now let's go down to letter D. In this one, I have two things under the radical. I have 8 times p, two things, which means that both of these terms need to be in my base when I write it as an exponential form. So just like over here, this is the exact same thing. I have to put both 8 and p inside my radical, like that. If I had just wrote it like this, that would not be the same thing because that would give me 8 square root p. So whenever you have multiple things underneath the radical, make sure you include them inside parentheses to indicate that that is indeed your base. Okay, and that was the first topic. If you're thinking back to that checklist I gave you at the beginning of the video, I said there were 3 topics. The first one was radical and exponential forms, being able to write them in radical form or being able to write something in exponential form. And now we're going to move on to nth roots. Now with nth roots, don't get thrown off by the name. N just means that you can put any number you want in there. Okay? So we've already kind of gone over this in multiplication and division rules. I can have x squared, I can have x cubed, I can have x to the 5th, x to the 100th, okay? I can have multiple things in my exponents, multiple numbers in that exponent box. In the same way, x to the 1/2 is not the only fraction that I can have in my exponent. Okay? I can also have x to the 1/3. I can have x to the 1/5. Heck, I can have x to the 1/100th. Okay, the denominator does not have to be 2. So now the question becomes, if it's not 2, how do you rewrite it in radical form? Well, if you look down here, you can see that you have the radical, and then whatever n is, it goes right above the check mark. This is also an indication as to how many repeat factors you're looking for. So when we were just dealing with x to the 1/2, okay, that meant we had the square root of x. There was a tiny invisible 2 right there. However, since the square root symbol means that you're looking for 2 factors, we ignore that little 2 and don't have to write it. Anything beyond the square root. So if you're looking for the cube root or the 4th root, you have to include however many factors you're looking for in this little box, that little spot. And that way you know, solving the problem, what it is you're looking for. This is the last big vocab word before we get started practicing. What happens when you're squaring numbers and variables or whatever is that 3 squared and negative 3 squared both equal the same thing, 9. 3 squared is 9, negative 3 squared is 9. Okay, which means that they're both square roots of 9 by definition. Okay, and the same thing as you go up the ladder. 2 to the 4th and negative 2 to the 4th both give you 16. So you have these 2 square root terms, these 2 solutions. The positive roots are called the principal roots. So that means that 3 and 2 are principal roots because those are the positive ones. Negative 3 and negative 2 would not be principal roots because those have the negative number up front. So if ever the book or an assignment asks you to solve for the principal root, you are looking for the positive number only. Now, as of right now, we're mainly dealing with principal roots, but as we get further on in the chapter, we will be dealing with the negative root. So you need to remember that when you square root something, you technically have 2 answers, the positive number and the negative number. Let's go ahead and practice. So we are just simplifying. Right now, if you're going off the checklist, this is still solving. So we need to simplify all of these radicals. This number tells us how many repeat factors we're looking for. So I'm going to do the same thing I did for the square root. I'm going to pull the 27 off to the side, and I'm going to break it down. I have 3 times 9, 3 times 3. And this time, I'm looking for a number that repeats 3 times, in which case 3 does it. So I'm going to circle the first one, and the other 2 go away. So my answer to the cube root of 27 is 3. Okay. Let's go over to letter B. I'm going to do the exact same thing, only this time I'm looking for a number that repeats 5 times. So I take 32. Now I'm going to split this up into 8 and 4, 4 and 2, 2 and 2, and then 2 and 2 over there. Okay, you're going to break up until you get more familiar with this whole process, go ahead and take all of your numbers down to prime factors. It may take a while, but it will really help you notice the repeat terms. Okay, so again, I'm looking for a term that repeats 5 times, in which case we have 1, 2, 3, 4, 5 2's. So the first one comes out, and the others go away. So my answer is 2. Video's going to pause. You guys do the next 2. When it plays again, you'll see the answer. And here you go. Now for 64, the odd thing about 64 is you had 2 groups, 2 sets of a number that repeated 3 times. Whenever you have this, whenever you have multiple things that come out of the radical, you always multiply them together. And the same thing happens is if you have multiple things staying inside the radical. You just multiply all those terms together and leave them inside. So now that we've solved nth roots, now we need to know how to rewrite them. So when we just had square roots, remember that we had the exponential form and the radical form. Well, if we had x squared, or x to the 1/2, that was equal to the square root of x. Same thing with our nth roots. We now have to learn how to rewrite them in exponential form and in radical form. The way it works is that whatever number is inside the check mark goes into the denominator of your fraction, and vice versa. Whatever number is in the denominator of the fraction goes into the little check mark. And then don't forget, just like last time, once you rewrite something in radical form, you still have to simplify to get your complete answer. So let's practice this. Here we go. First, I'm going to rewrite my terms. So the number that's in the denominator is going to go in the little check mark. So I have the cube root of 125. Now I need to simplify. So pull 125 out to the side, and I'm going to break it down. 5 times 25, 5 times 5. I'm looking for a term that repeats 3 times, and in this case, 1, 2, 3, 5 repeats 3 times. So I'm going to circle the first one, and the other 2 go away. My answer is 5. You guys go ahead and try the bottom 2, rewrite it as a radical form, and then simplify. And here are your answers. Now you may have noticed that going all the way down to the prime factorization of numbers can get a little long and can waste a lot of paper. It really does help if you know your prime factors, because then, as I did in 3B, you can just shorten it. Okay, I knew that 126 or 156 was 4 times 64. I knew that 64 was 4 times 16. Okay, so I'm leaving the 4 alone and I'm continuing on. 16 is 4 times 4. That's a prime factor. I didn't have to go all the way down. I didn't have to break all my 4's down into 2's because I recognize that there are 4 4's within here. Now, you just learn this by practice and going over it and over it and over it again. But the faster you learn your square roots, the easier these factor trees become and the faster they go. All right, this is the last little category under nth roots. In my checklist at the beginning of the PowerPoint, I called this the complex roots slide. In the last one, we talked about what happens if the denominator changed. So instead of having x to the 1/2, we now can have x to the 1/3. In this slide, we're now talking about what happens if the numerator changes. And that's what I mean by complex. We now have a more interesting fraction. The way this works is the denominator still goes in to the check mark, but the numerator, I'll change colors for this one, the numerator behaves like a normal exponent, like we've been doing this whole time, and it goes to the outside or to the regular exponential spot within the radical. Okay? Best way to recognize that is just to look at it and see the difference. Now, both of these are valid. Both of these are equally true. The only difference between why we would write one over the other, so let's say the first one over the second one, is convenience. There will be some problems where writing it the first way makes your problem a lot easier and makes it simpler to solve. There will be other times where writing the problem the second way will make it easier to solve. For right now, I'm going to use the first way. But keep in mind, both ways are equally valid. So going down here to the example, I have 8 to the 2/3. My 3 goes into the check mark. That's my denominator. My denominator always goes into that little check mark spot. My numerator always goes, or for right now, will go outside of everything. So you're going to put the entire radical inside parentheses and your numerator on the outside. Let's practice. Here we go. First, I'm going to rewrite. So I'm going to have my check mark, my square root symbol. My denominator goes in the check mark. My base goes underneath the radical. Keep that in mind. I haven't really made a big deal out of it right now. But remember, your exponent only applies to the base. So as we get into the more complex problems, that'll be a thing. Next, the numerator goes on the outside. Now, just like beforehand, you still have to simplify your radical. So I'm going to pull 64 out over here and break it down. By now, you should be familiar with this number. So my answer ends up being 4. This one comes out, these two go away. Now 4 is going to go inside my parentheses. So this simplifies to 4 squared. Then we need to continue simplifying. We're not done yet. So your overall answer is 16. And that's your final answer. Let's do another one. Come down here. I'm going to rewrite it first. Don't try to solve until after you've rewritten. Things can get really complicated really quickly if you do it otherwise. My base goes inside my radical, my denominator goes in my check mark, and my numerator goes outside. Next, I'm going to break down my base. Break down whatever's inside the radical symbol. So I have 27, 3 and 9, 3 and 3. So 3 is my answer. It's going to go inside my parentheses. 3 squared. Now I need to continue simplifying, and I have 9 as my final answer. Your turn for 4B. Now, what I want you to do, don't get scared by the big numbers, either by the giant base or by the 5 and the 4 in your exponent. When you're squaring things, numbers get big really quickly. When you're taking the square root of things, numbers get small really quickly. So don't ever get scared when you see a big number. Just calm down, go through your factor tree slowly and carefully, and you'll be fine. Okay, video's going to pause, and when it plays, you'll see the answer. Okay, so in this case, you did end up with a pretty big number. But if you went through it slowly and carefully, it comes out pretty nicely. If ever we're going to deal with these monster numbers on a test or quiz, I will allow you to use a calculator. But for all of the smaller exponents, even the 4s and the 5s, that's fair game without a calculator. Last bit of the PowerPoint. Sorry for the long video, but we're almost done. If you're paying attention to my checklist, solving exponential equations is the last little bit. So far, all we've been doing is simplifying numbers. We have yet to put x anywhere in here. It's been lonely. Welcome back to the floor, x. So what happens, essentially, when you have an x in the exponent? This is now an exponential equation. And you can see the definition right there. Now, the way we're going to solve this is to make sure both of our bases are the same. Okay, that is the goal. Our goal is to get the base to be the same. Because once the base is the same, as you can see down here, once the base is the same, they kind of go away, leaving only the exponents. Now that's what's happening right here. We have 5 to the x power is equal to 5 to the third power. Since the bases are the same thing, they go away, leaving only x is equal to 3, which would be our answer. All right, let's go ahead and practice because this one just makes sense if you see it. And here we have it. Now these look a little scary, but we're going to go through it slowly and it'll make sense in a bit. Now, the way we solve this problem is to get x out of the exponent. Right now, our goal then is to get these two numbers to be the same. Okay? Over here, we have a base of 6 to an exponent. I need to get 216 to have a base of 6. Now, what I mean by that is I need to find what 6 times a number, or 6 to the power of a number, gives me 216. So I'm going to break this number down. I have 216, and since I know my base has to be 6, I'm going to just start dividing by 6 and see what that takes me. So this is 6 times 36, which means I have 36 breaks down into 6 and 6. So I have 1, 2, 3 6s. So that means I can rewrite this whole thing, and I can rewrite 216 as 6 to the power of 3. Which means my bases then go away, and x is equal to 3. So what we just did here is our goal was to rewrite this big number so that it was a number to an exponent. I used 6 as my goal. That was what I already needed to have, because if the bases are the same, then they go away, and that's awesome. So I divided 216 by 6 to see how many times I multiplied 6 by itself to get this number. Let's go on to letter B. Now letter B is a bit more complicated, but the same logic applies. I have the base of 5 over here. This is technically 5 to the 1. So my goal is to get this number to also be a base of 5. Okay? Well, 25 is nice because we already know that 25 is equal to 5 squared. So I'm going to rewrite 25 as 5 squared. So I have 5 squared, and then I'm going to put in the rest. I'm going to carry down the rest of my exponent, x minus 1. So my original exponent doesn't go away. It actually gets multiplied by that 2 in a minute. Equals 5 to the 1. Since my bases are the same, they go away, and I'm now left with 2x minus 1 is equal to 1. Now this is an equation I can solve quite easily. And so I'm going to do that. And here's your answer. So as you can see, you can have x be a nice number or you can have x be a weird looking fraction. But whenever you're solving exponential equations, the number one goal is to get both sides of the equal signs to have the same base to an exponent. We'll go over this one again in class because this does take a few times through it. But that is the end of this video. Thank you very much for your patience on this long lesson, and I'll see you next time.